Sorting algorithms are methods of reorganizing large number of items into some specific order, such as highest to lowest, or vice versa, or even in some alphabetical order. We have so many sorting algorithms designed over a period of time, mostly to improve upon the previously designed algorithms. Now we will study and analyze these algorithms one by one, and the first one that we want to talk about is selection sort. Selection sort, in my opinion, is the simplest sorting algorithm, and this is what anyone would do intuitively. Now let's say we want to write a program to sort a list of integers given to us in the form of an array, something like this. Given an array of 6 integers, and we have indices from 0 to 5. To sort this list, we can create another array of same size as A. So we have another array of size 6, let's name it B. Now we can start creating B as a sorted list by selecting the minimum from A at each step. There will be multiple passes on A. In the first pass, 1 will be the minimum, so 1 will go to the first position in B, which is index 0. Now there should be a way to mark that 1 has already been selected, so it's not considered in the second time. We can do this by placing the selected element by a very large integer, which is guaranteed to be the maximum in the list. We can choose the maximum possible value in 32-bit integer, which is 2 to the power of 31 minus 1. Now we will scan the list again to find the next minimum value, which is 2, and it will go to the second position in B, which is index 1. Again we will replace it by the maximum value, and we will go doing this until all positions in B are filled. In the end, we can copy the content of B back to A, so A itself will be sorted. This logic will work fine, but as you can see, there is extra memory requirement for this temporary array B, which we created. And the larger size of array A, the larger extra memory required for creating the temporary array B. So this is not an in-place sorting algorithm. An in-place sorting algorithm takes constant amount of extra memory for sorting the list. So let's see how can we solve this with an in-place sorting algorithm without creating the temporary array. Here is the list we want to sort again. What we are going to do now again is searching for the minimum element in the array, so we will scan the whole list to find it. The minimum is 1. Now instead of filling 1 at index 0 in a temporary array B, what we can do is swapping 1 with element at index 0. Because 1 is the minimum, so that's where 1 belongs. So 1 goes to index 0 and 6 comes to index 2. Now we need to look for the next minimum value, but 1 is not considered. As you can see, now it's easy. We don't need to replace 1 by a maximum value. All what we need to do is, instead of starting searching for the minimum from index 0, we will start from index 1. The minimum is 2 at index 4. Now 2 must be at index 1. So 2 goes to index 1 and 9 comes to index 4. Again we will look for the next minimum starting at index 2. The minimum is 3 at index 5. So we will swap it with element at index 2. So 3 goes to index 2 and 6 comes to index 5. And it will go on like this until we have our list sorted. This particular in-place logic of selecting the minimum at each pass and putting it at its appropriate position is selection sort. Now let's write pseudocode for this algorithm. We will write a function named selection sort. This will take an array and the number of elements in the array as arguments. We will run a loop starting from I equals 0 till n minus 2, and in each iteration of this loop we will set the minimum. Let's name it I min. So first the minimum will be at index 0, and then we will put the second minimum at index 1, and so on. We can say that the first element is the minimum, and we will scan the array from I till n minus 1. If you find an element which is smaller than I min, we will update the minimum by replacing it with the new minimum value. Let's write our loop. So For g equals I plus 1 to n minus 1, and while scanning, if you find a of j lesser than a of I min, we will update the minimum. Now, when we come out of this second loop, I mean we'll have the position of the minimum value in the list. So we will swap it with the element at index I. We will do so by using a temporary variable. And this is how our function will look like. We will quickly run this logic in real C program. I have written this function selection sort. In the main method I have created our previous array which has 6 elements. Then I'm calling the selection sort function, passing the array and the number of elements. And once I have sorted the array, I'm printing the elements. The time complexity of selection sort is big O of n squared. We can quickly see how. The running time is the total running time of all the statement. Let's say this statement will take a constant time c1 to execute. This statement will take c2 to execute, and let's say this statement will take c3 time to execute in the worst case. This particular statement will run exactly n-1 times. This will also run n-1 times. If you try to calculate how many times those two lines will executed, it will be n-1 for I equals 0, n-2 for I equals 1, n-3 for I equals 2, and this will be an arithmetic progression. We'll go till 1 for I equals n-2, and this will be only equal to n multiplied by n-1 upon 2. So overall time taken will be something like this. And if you evaluate this, it will be some polynomial like an squared plus bn plus c, where a, b, and c will be some constants in terms of c1, c2, and c3. And whenever we have a time expression like this, it belongs to the set of big O of the highest order term in the polynomial. So this particular polynomial belongs to the set of big O of n squared. Selection sort is a slow sorting algorithm. Big O of n squared is not the best finding time for a sorting algorithm. So this was selection sort algorithm and its time complexity analysis. We will discuss more sorting algorithms in the coming lessons.